Imagine stepping into an elevator, pressing a button, and finding yourself not on the top floor of a skyscraper, but in the orbit around Earth. This isn't a fantasy from a sci-fi novel. It's a concept that's been captivating scientists, engineers, and dreamers for over a century. Today, we're diving into the realm of space elevators, a technology that could revolutionize our access to the cosmos. What if we actually built one? How would it work, and what challenges would we face? Let's embark on this vertical journey and explore the possibilities that could redefine our relationship with space. The idea of a space elevator isn't new. In 1895, Konstantin Tsiolkovsky, inspired by the Eiffel Tower, first conceptualized a tower reaching from Earth's surface to geostationary orbit. His vision, though ahead of its time, laid the groundwork for future thinkers. It wasn't until 1957 that Russian scientist Yuri Artsukhanov proposed a more practical design, using satellites as a counterweight. This concept was further redefined by American engineer Jerome Pearson in the 1970s. However, it wasn't until the discovery of carbon nanotubes in 1991 that the dream began to seem achievable. These microscopic structures, with their incredible strength-to-weight ratio, offered a potential material strong enough to construct such an ambitious project. Since then, interest in space elevators has grown significantly. NASA has conducted feasibility studies, and organizations like the Japan Space Elevator Association have been founded to promote the development of this technology. At its core, a space elevator is a cable anchored to the Earth's surface extended into space. The other end is attached to a counterweight beyond geostationary orbit, using centrifugal force to keep the cable taut. Climbers, essentially specialized elevators, would traverse this cable, carrying payloads into space at a fraction of the cost of rocket launches. To understand the feasibility of space elevators, we need to grasp a few key concepts. Geostationary orbit. An orbit 35,786 kilometers above Earth's equator, where satellites remain fixed relative to the ground. This is crucial for maintaining the elevator's stability. Tensile strength. The maximum stress a material can withstand while being stretched before breaking. This property is paramount for the elevator cable, which must withstand enormous forces. Carbon nanotubes, cylindrical molecules of carbon atoms with extraordinary strength-to-weight ratios, potentially ideal for constructing the elevator cable. Coriolis effect, the apparent deflection of moving objects when viewed from a rotating frame of reference. This would affect the elevator's movement and need to be accounted for in its design. The most immediate impact would be economic. Currently, launching payloads into space costs thousands of dollars per kilogram. A space elevator could reduce this to mere dollars per kilogram. This dramatic cost reduction could open up space to a wide range of commercial and scientific endeavors. Imagine solar-powered satellites beaming unlimited clean energy to Earth, or asteroid mining operations bringing rare minerals back home. The global energy landscape could be transformed, potentially solving both our energy crisis and resource scarcity issues all in one fell swoop. Space tourism could become as common as international flights, with hotels orbiting Earth and lunar vacations within the reach of the middle class. This burgeoning industry could create millions of jobs, from space hotel staff to orbiting tour guides. The reduced launch costs could also revolutionize satellite deployment. We could use a proliferation of communication satellites, enhancing global connectivity and potentially bringing high-speed internet to every corner of the globe. The ease of access to space would accelerate scientific research exponentially. We could construct and maintain large space telescopes, enhancing our understanding of the universe. Imagine a telescope array spanning thousands of kilometers in space. offering unprecedented views of distant galaxies and potentially habitable exoplanets. Microgravity experiments, currently limited by the International Space Station's capacity, could be conducted on a much larger scale. This could lead to breakthroughs in material science, with new alloys and crystals that could only be formed in zero-G. In the realm of medicine, we might see advancements in drug development and treatments for conditions like osteoporosis, taking advantages of the unique properties of microgravity. The biological sciences would also benefit greatly. We could study the long-term effects of low gravity on plants and animals, paving the way for sustainable space colonization. Experiments in astrobiology could help us understand the potential for life on other planets and how terrestrial life might adapt to extraterrestrial environments. A space elevator wouldn't just revolutionize Earth's orbit operations, it could serve as a launching pad for interplanetary missions. Spacecraft could be assembled in orbit, free from size and weight constraints of rocket launches. This could pave the way for larger, more ambitious missions to Mars and beyond, potentially accelerating our journey to becoming multi-planetary species. Imagine massive generation ships being constructed in orbit, designed for long-duration flights in the outer solar system or even nearby stars. The elevator could facilitate the transportation of materials and personnel needed for such ambitious projects. Moreover, the elevator could serve as a starting point for a network of similar structures throughout the solar system. A space elevator on Mars, for instance, could dramatically simplify colonization efforts and resource extraction from the Red Planet. While space elevators promise cleaner access to space compared to rocket launchers, they're not without environmental considerations. The construction process would be massive, potentially disrupting local ecosystems, especially if built on land. However, the long-term benefits could outweigh these initial costs, especially if space-based solar power becomes a reality, helping to combat climate change. The elevator could also play a crucial role in Earth's observation and climate monitoring. With easier access to various orbital altitudes, we could deploy a network of advanced weather and climate satellites, enhancing our ability to predict and mitigate natural disasters. There's also the potential for space-based geoengineering projects. While controversial technologies like solar shades to combat global warming could become more feasible with a space elevator, the location of a space elevator would become a point of significant geopolitical importance. It would need to be built on the equator for optimal positioning, likely on a floating platform in the ocean. This could lead to new international agreements and potentially reshape global power dynamics. Countries hosting or controlling access to the elevator would gain significant political and economic clout. We might see the rise of new space powers not traditionally associated with space exploration. The elevator could also necessitate new forms of international cooperation. Its construction and operation would likely require a global effort, potentially fostering better relations between nations. However, it could become a source of conflict if not managed carefully. The existence of a space elevator would fundamentally alter humanity's relationship with space. Space travel could become commonplace, leading to a shift in our collective perspective. The overview effect. The cognitive shift reported by astronauts upon seeing Earth from space could become a widespread phenomenon. We might see the emergence of a new subculture and communities centered around space habitation. Spacers, or elevators, could become distinct societal groups with their own customs and perhaps even physical or psychological adaptations to low-gravity environments. Education would likely see a shift towards space-oriented curricula, preparing the future generations for life and work beyond Earth. New fields of study would emerge, combining disciplines like architecture, biology, and engineering to address the unique challenges of space habitation. Of course, building a space elevator isn't without its hurdles. The primary challenge lies in material science. We need a material strong enough to withstand the immense tensile forces involved. While carbon nanotubes show promise, we're still far from producing them at a necessary length and quality. Other challenges include space debris. Even small objects can sever the cable if they collide at high velocities. We would need advanced debris tracking and mitigation system. Weather. The lower portion of the cable would be subject to wind and lightning strikes. Engineering solutions to withstand these forces would be crucial. Radiation. Climbers and passengers would need protection from cosmic radiation, especially in the Van Allen belts. Logistical complexity. Maintaining and operating such a massive structure would be an unprecedented engineering challenge. We'd need to develop new technologies for inspecting and repairing the cables in space. Security. The elevator would be a prime target for terrorism or military actions. Protecting such a large stationary structure would pose unique security challenges. Legal and regulatory framework. New international laws and regulations would be needed to govern the use and operation of the elevator. The concept of a space elevator stretches the limits of our current technology, but it's not outside the realm of possibility. If we manage to overcome the hurdles, particularly in material science, we can be looking at a future where space is no longer the final frontier, but our new backyard. As we've explored, a space elevator could revolutionize our economy, accelerate scientific discovery, and reshape our relationship with the cosmos. It could be the key to becoming a true spacefaring civilization, opening up possibilities we can hardly imagine today. But what do you think? How would your life change if you can take an elevator to space? What new industries or scientific fields might emerge? And perhaps, more importantly, are we ready for the responsibilities that come with such easy access to the stars? As we continue to push the boundaries of science and engineering, it's clear that the sky is no longer the limit, it's just the beginning. The space elevator concept challenges us to think big, to collaborate on a global scale, and to reimagine our place in the universe. In the end, whether we build a space elevator or find another path to the stars, one thing is certain: our future lies not just on Earth, but in the vast expanse of space that surrounds us. It's up to us to reach out and grasp it. If you like this video and want to see more, like, subscribe, and hit that notification bell so you can always be caught up. Until next time, this has been All Sci Fi What If.